Hello, this is a special one. This is not in my room, but anyway, so this is the next things that we have to talk about these chapters. This chapter is about how can we use GPIOs to control our IC pins, right? And before this time, you know exactly that we can use our C language combined with the assembly for the startup code. Then by link everything together, then we can generate the output like in the examples that I give you last time. That this is the example that I define everything in C, then just use step by step to change the speed of your CPUs from 8 megahertz to 72 megahertz. Okay, that is we talked about last time. But as you know, in this one is not quite it's hard to produce the output by yourself, right? Because it's a little bit complex. This one is very useful when you would like to try to do some code without any standard libraries that help you. Like in these times, like when you go through the internet and you will find out the new CPUs, then this is the best way you combine assembly language and C language in order to control your microprocessors. Okay, but if we have any different methods in order to develop the code using C language, yes, of course. Different methods we call the standard peripheral libraries. Okay, we talked about this one a little bit before, right? And what is the difference between the standard peripheral libraries and the C that we programmed last time? The main difference is the standard peripheral library is provide you the API or the functions that you can control every single things that happen into your CPUs. Such as if you would like to do something with your RCC register group, then they provide a lot of API or a lot of functions that you can use in order to control most of the other things. And one more thing that is very useful for you is they already define the address for every single registers inside your CPUs. It means that when you would like to use GPIO, it's very simple because they already define. You just call the name that they use like a standard name for your code. Then you can control GPIO very easily. Okay, that is a point that we have to talk about today. Okay, first of all, we have to reproduce the same behavior of our CPUs using our the standard libraries for for ARM Cortex M3s, right? Then we have to involve with two things. First, we have to involve with the RCC group because this one is used to control the clocks and also they provide or enable clocks to our peripherals. Then we have to know the standard API for this group. Then what else we have to know? We have to know the standard API for GPIO because we would like to use GPIO as output to our maybe LED or 7 segments. Okay, first of all, let me show you the APIs for RCC group. For the RCC group, there are plenty of the libraries, but how can you find the standard peripheral library reference? Okay, you can go to the website for your CPUs or the websites that give you the manufacturing companies. Then they will provide this one is SPL reference that you can see what is the name of the functions and what this function do to your CPU. Let me start with RCC dint, the first one. Okay, I don't have my pen today, so I just use as a laser pointer here. dint. So this one, what gonna happen? If you call these functions in your main program, they will erase every single thing for your CPU, such as if you just boot your CPU up by using standard peripheral libraries. In the boot up code, they just assign some value to your RCC group, and from the boot, then they change the speed of your CPU from 8 MHz to 72 MHz for you already. So if you would like to use the other things, such as if you would like to change from 72 MHz that generate from the HHI to HHE, sorry, to maybe 48 MHz that generate from HHI, so you have to do it initialize first. Otherwise, you cannot do anything. Okay, by using this one, your CPUs will start to use HHI at 8 MHz. Then we have what we have. We have HHE configurations. For HHE configurations, the function will configure HHE for you is external high-speed oscillation, right? So you can use HHE configurations to configure your externals high-speed oscillation. Okay, so what else do we have? We have wait for HHE startup. Okay, this one is like our time, like the last time that after we change the parameters inside your RCC group, then you have to wait until that function is ready to use. In this case, they create functions to check HHE's status, right? Then if the function is show the information that HHE is ready, then they will return true. Then you can go through your code, then the next line of your code. Then what do you have? You have HSI command. For HSI command, you know exactly HSI is internal, right? Oscillations. This one is used to enable or disable HSI, because when you change from HSI to HHE, then if you still open HSI, so it's consume a lot of energy because you still have some oscillation inside your CPUs. Then what else do we need? Do we have for this group for SPL for our ARM? Then we have RCCL PLL configurations. This one used to configure your PLL, like you select the source of your PLL module, and also you just find the value of multiplications for your PLL, such as multiply by 9, multiply by 6, multiply by 16, whatever that your PLC can configure. Okay, then we have the PLL command here. This function is used to open, disable or enable your PLL. Then you have the sys clock configurations, and this one, what is it actually? This one is configurations that you will say what the clocks that your CPU would like to use. In this case, you have 3 clocks, like the first clock is HSI, then you have HSE, then you have PLL clock. These functions will configure your systems to use one of these 3 sorts. It depends on you. What else? This one, you have the functions that get the values of your system clock. Okay, in this one, they will use to read the sort of the system clock for use. What else? In this one, you have the RCCH clock config. So what is it? This is define the pre-scalars for your system. So you just you would like to divide your speed of your systems. This one is used to generate HB bus, or maybe we call high H clock that generate and fed into your systems. Okay, you can divide by 4, 8, 16, whatever. It depends on your speed, right? But most of the time we didn't use we did not divide this HHB clock, because this HHB clock can go up to 72 MHz, such as your system clock. So we just leave it like that. Or you just set divide by 1. In here you will find out this is parameters. So what is a parameter? Parameter is mean that you just put this word into the functions, then it's generated for you. For the examples, if you use RCC H clock config, then you just pass parameter RCC 6 clock divided by 16. In this one, then your program will divide your system clock by 16 and then generate HHB by using that frequencies. Or you can do this one, HHI command, and you just give enable or disable into these functions as a parameters, then they will enable or disable your HHI. As you can see here, it's very useful and understandable and easier to follow, right? Okay, we move a little bit to the next one. What we have here, we have Peacock 1 and Peacock 2. So for this Peacock 1 and Peacock 2, for Peacock 1 is the clocks for APB1 bus, and for APB2, then we have Peacock 2. Then you can specify the parameters such as you would like to divide by 1, divide by 2, divide by 4, divide by 8. It depends on your speed, right? So most of the time we just use APB2 as fast as AHB bus, but for APB1 we have to divide, right? Because the maximum speed is just 36 megahertz. Then we can select RCC SC clock div 2 or divide by 2 as a parameter into these functions. Then voila, you will have APB1 bus at 36 megahertz if your system clock is 72 megahertz. What else? For this one, I did not want to cover for now because in this one, we have to deal with something called RTCs or real-time clocks. This one is used to provide the real-world watch for your system. We will talk about it later in the maybe next chapters. Okay, what else do we have? We have RCC APB1 peripheral clocks command. So this one is just used to configure which peripheral module you would like to use. Then by using this one, you can provide a clock to your peripherals module that connect to AHB1 peripheral clock. Okay, they have APB2 peripheral clocks and also APB1 peripheral clocks command. And for APB2 peripheral clock command, it means that if you just pass through these parameters, they will open that peripheral for you. Such as in this case, we would like to open our GPIO-C or GPIO-A. Then you just give the parameter RCC APB2 peripheral GPIO-A or GPIO-C into this function. Then this function will enable your GPIO-A or GPIO-B for use. And if you would like to use other things such as timer, SPI, UR, you can specify by using this one. And one more thing, if you would like to open more than just only one peripheral, such as you would like to open a GPIO-A and also in the same time you would like to open GPIO-B, you can use all operations, such as you just pass through parameter inside this function using RCC APB2 peripheral GPIO-A or RCC APB2 peripheral GPIO-B or RCC peripherals to APB2 peripheral GPIO-C, and you will see this in your code. In the code, don't worry about that, but I would like to explain. And for how about RCC APB1 peripheral clocks command, and this one is do the same things for your ACC APB2 peripheral clock, but this is connect to different peripheral for you, right? Because this group is slower than the first group in our peripherals. So you just can specify the names of your peripheral, then you just pass to the function and your functions will enable that peripheral for use. Okay, what else? We have ADC command, and this one they will say this is a divisions for ADC clocks command. We will talk about this later when we go through our ADC chapters. And if you don't remember, ADC is analog to digital converters module inside our CPUs, and this one we use to convert the real world signals to digital versions that represent that informations inside your CPUs in digital world. Okay, so let we go through our examples or APB or configuration RCC. Okay, the first one, if you use RCC HHE configurations and we pass RCC HHE on, it means that right now you would like to open your HHE. Then you can do RCC configurations, PLL configurations like this one. And when you use PLL configurations, you can show the system that which is the input for your PLL. In this case, you use parameters RCC PLL sort underscore HHE div1 is mean that you would like to use the frequencies that provided by HHE, and this is the input for your PLL module. Then you pass the other parameter is called RCC multiplies by 9. It means that your PLL will multiply your frequencies of HHE by 9 times. Then we can open our PLL by using this command RCC PLL command, and we pass parameter enables. Then your system will enable PLL module and it start to generate the high frequencies for your systems. And you can take a look here. You can do a lot of things, such as you have to do some configurations, and this is you would like to divide your system clock or H clock by 2 and provide to P clock 1 or APB 1 clock, and this one is not the same. And for to open your GPIOs, as I explained you before, this one is use RCC APB2 for referral clock command, and you just pass two parameters. First is RCC APB2 for referral GPIO-A. Next one is GPIO-B, and you can combine together using OR. In this one, it's just byte. Then you pass the last parameter here is called enable. It means you would like to open your GPIO-A and GPIO-B for your systems. Okay, then we move to the second group. The second group they will call structures in order to use this one. Why? Because if you go through GPIO, right? GPIO consists of a lot of registers in the group. Then they combine everything together and create a new class or a new group. If you know the object oriented, right? The new class is called GPIO type def. Then by using GPIO type def, then we can access every single registers that belong to the GPIO that we concerns. In this case, if you just do GPIO-A, then they have the structure for whole GPIO-As. So as we know, we have a register called CRL. We have the register called CRH, right? And we have the register called ODR that we used last time. They create the structure for GPIO type def for you, and you can call this one as the new variables. Then you can use that variables as the way that you control your GPIOs by using like a class. Okay, so in this one, if you would like to know how it works, basically, if you go through STM32F10X underscore map.h, and GPIO will define as GPIO A, B, C, D with a base. And in the base, if you track back a little bit, you will find out that just provide the beginnings of your address at the beginning of the GPIO group. Then by using that we use last time, what we used last time to find the actual address for your registers. Okay, if you did not remember, I just show you again last time, right? Because this one, as we know, we will find out that they just provide the base, then they add something called offset. by using the type group that you define a new type as a object oriented here, then you don't have to care about the locations or address of this register. Why? Because if you take a look here, they define the variables for each register name by using a Valentine and size 32-bit. It means that each one is what? It's 32-bit, right? For it means that there's step for address, and if you take a look here, every single register inside your GPIO group, they just go through one by one just for address. Okay, so you don't have to find the exact value for your address anymore by using these structures. Okay, so what is your standard peripheral library for GPIO X? Oh, as you know, X can be A, B, C, D, E. It depends on your systems. They have GPIO initialize here, and this one they just force your GPIO back to the original value for every single register inside your GPIO group. And if you know this one, if you would like to know what is the start value for your GPIO, you can take a look on your datasheet. Then you will find out for each registers what is the default values. Then you will use something called GPIO initialize, and this one you can pass informations to these functions to configure your GPIO. In this case, as you can see, we can configure like a GPIO pin, which pin we would like to open, and what is the speed of that pin, and also what is the mode of that pin. Can that pin be input? Can that pin be output? And you can specific GPIO X into this one also in order to use different GPIOs in your systems. What else? The next one is called GPIO structure initialize. This one will create the structures that you would like to put into your GPIO initialize functions. We will go through this this function later. Okay. Then what else? If you would like to read or would like to write or you would like to display something to your GPIO pins, it's very simple. They can use these functions that read input data bit, read output data, read output data bit, and read output data. And this one, as you can see, you can read the IDR registers or ODR registers. Okay. Okay, what else? What else we have a GPIO set bit, and this one will change the logics of that IC pins into 1, because set it mean 1 in digital world. So how about reset? Reset is do different things. They just change by using these functions. They can change the values from whatever's into logic zeros for use to that specific GPIO pins. As you can see in this one, you can pass also a GPIO X. It means that you would like to make all the output to be zeros, or you can specific just single input or single pin such as GPIO 0, GPIO 1, GPIO 2. It depends on you. So this one is very useful tools to change the logics of your GPIO. What else? You have the write bit and also a write functions, and you can take a look here. Then what else? This is called remap configurations. I would like to talk about this one a little bit. In this one, if you go through your datasheet for Cortex M3s, you will find out there are the default functions for each pin inside your microprocessors. It means that GPIO A0 can be this and can be that. But if you find out it is very hard to create your PCBs or schematic using that default configuration for each pin, then you can use something called remap functions. For the remap, they will allocate the pin differently But how can it's different? We have to take a look on datasheets, and they will say such as if you did not do anything, GPIO-A can be TX, GPIO-A 1 can be RX, GPIO 0 can be TX. But if you use some remap, GPIO-A 0 can maybe do a different function else, such as become I square C, or GPIO A0 become something else. Okay, that is called pin remap configurations. We don't worry about that one for now, because we didn't remap a lot. Unless you would like to create your own specific your PCBs, then you have to do a lot of remappings. Okay, this is the examples how can we use API for GPIO-X. In this one, first of all, we can just if we would like to make a GPIO-B to be the default value, then we use GPIO-D initialize and pass GPIO-B values into these functions. Then they will make your GPIO-B as the original value or default value. Then if you would like to do configure your GPIO, then you have to do create a new variable. It's called GPIO initialize type def. Then you just create the new structure is called GPIO initial structures. Then for the GPIO initial structures, you can go through GPIO pin by using a dot. Okay, this one is structure, right? If you would like to change the value inside that structure, you have to use dot. In this one, we would like to select which pin we would like to use in our projects. In this case, we say that GPIO 0 we will use GPIO 3 and GPIO 4. By using this one, this structure know exactly this is a pin that we would like to enable. Then we can use dot GPIO speed to specify the speed of your CPUs, your pins. In this case, we select speed of 50 megahertz because this is maximum, right? Okay. Then what else? Then we can select the mode of GPIO mode here. Then right now we use GPIO as a GPIO mode out, it means the output, and we follow by PP. PP is for push-pull configurations. If you don't remember, you can go back to the previous previous videos that I already explained what is the mode for our GPIOs. Then you use GPIO initialize and pass through the GPIO that you would like to configure, and you just use these structures, and then that GPIO will act like your GPIO structures. But this time you have to pass by, and here is mean pass by address, because right now our GPIO initial structures here is a variable, right? It's a class, so you have to pass the values, or you just pass the address. Then they will do some process that change the values inside your GPIO-A here. By using this command, you will find out your GPIO-A pin 0, pin 3, and pin 4 will enable, and every pin is a mode out, and is a push-pull output mode. And the speed of the pin 0, pin 1, and pin 3 will be 50 Hz. How about the other pin that you did not define? They will leave as the defaults, and that's it. Okay. If you would like to read the values from your GPIO pin file, then you can use these commands. It's GPIO read input data bits, and you can specify that this is a pin number 5, and you would like to use to read pin number 5 on GPIO here, then you get the value here. How about if you would like to change the bit? In this one, if we use set bit, then we specify which GPIO we would like to use. In this case, we use GPIO A. Then we specify that GPIO A pin 3 and pin 4 will be set, it means become 1 logic. How about reset bit? Okay, you can take a look here. It's very simple and straightforward. And most of the time, if you would like to control all your GPIOs, then you can use the last command line here is called GPIO, right? Then you just specify the GPIO that you would like to use. In this case, you use GPIO A, and you follow by the values. In this case, you just use 16-bit, right? Because GPIO can have up to 16-bit, and you specify the value 0x1101 to that GPIO A. Then your GPIO A will become 0x1101. Okay, this is the standard libraries that you can use in order to develop your software for your microprocessors. But because of this one, you find out you have to use a lot of standard peripheral library, right? But how can you do it? If you just go back to your C programming, you will find out it's not convenient at all, because there are plenty of things, and if you just download your standard libraries to your PCs and you would like to use all of that one, you have to compile to create object file and link everything together and create your own boot up or startup code by using your assembly language. So by using the peripherals libraries, I would like you to change your software from the command line that you try in the GCC for your ARM on AGB whatever into IDE, Integrated Development Environments. So we will use something called Atolic through Studios at our IDEs in this one. I think you already installed to your systems. Then you just double click it and it will show this screen. And if you wait for a while, you will find out they will ask for the working directories. And this one you can use as the default, or you can store your code in somewhere else. Just select the workspace location for your projects, then you just click OK, then you create a new project for you. Okay, you have the environment already, so you have to specify the names, or you have to create a project. So the project will consist of your main program, boot up, load linkers, loaders, whatever, and also the standard peripheral library for use. Then you just click on File, Next, and See Projects. In the C projects, you will find out there are plenty of it. You just specify the name. In this case, I specify as the test one is the project names. Then I just select the project type to be embedded C projects, and I use two chains is Autolic's ARM tools. That in this one, if you take a look inside there, the ARM GCC, ARM AS, ARM LD, object dump, whatever. This one you can change to GCC that we talked about it last time, or you can stick to Atolic ARM2. That's fine, because you will get almost the same output in hex file that you can use for your systems. Then you click Next. Then they will ask what is your CPU that you would like to use in this project. For our projects, you have to select STM32F1 series, and you did not select a board, you select a CPUs, because our board is not belong to the to this software, okay, because it's not officials that came from the manufacturing companies. You just select the CPU, and you select your CPU that you use in your board is STM32F103CH. Okay, and you click Next. Then they will ask you would like to use the runtime libraries, what is it and why you use it. Actually this one you don't have to do anything, you just can click Next. But I would like to show you something that if you would like to use some functions called printf, sprintf, or sprintf, then by specific new library nanos, it means that your code is very small size when you compile the printf and also sprintf. Okay, if you don't know this one is consume a lot of memories used in order to create a code for printf, sprintf, and sprintf. Therefore, they create their own versions that are like a better versions is use less memories in order to use these functions. You can stick to your defaults and you just click Next. And last thing that you have to define is called True Studio debug configurations. For our case, we use ST-Link and we click finish. And don't worry about this one. Because you did not connect ST-Link directly to your software, you have to create your binary file, then you just directly program it using ST-Link software. Don't use ST-Link directly to your True Studio IDE because it's a little bit complex in order to use it. Just click finish, then they will create a project for you. That in your project there are plenty of things that give it to you, such as they have STM32 flash.ld, and we know exactly from the last time that .ld is the linker script, right, that explain the structures of your memory inside your CPU, and this one they're specific for you. Then what else? They will have a lot of things that show in here is a startup code. Here's so if you would like to take a look what is your startup code, you can take a look into .s. This one is assemblies. Then they will have a lot of including file and header file here that will help you to do a lot of programming easier. Then what else? The main object is to change the value inside your main.c, and the main.c is the main program that you have to write down your own code. What else? The powerful things for SPL or standard peripheral library will show will included inside the folder libraries here, as I show in here. Then they will create a project and they will build your project for the first time. This one can take 1 or 2 minutes. Don't worry about it. It depends on your speed, CPU speed. Then this one will end up with complete compile. So what actually they try to do, because of, as you can see, they are involved with a lot of C and a lot of S file, and if you would like to connect everything together, then you have to compile one by one in order to create on an object file or .o file, right? And this one they will find out which one is not meant to be altered, then they just compile to be an object file. And next time, if it already have .object file, they don't recompile again, then you can compile your code faster using this way. And when it finished, they will find out, okay, our project is test 1 each build file done and build report done, and everything taking about 17 minutes in my computers. Okay, and if you take a look inside your main.c, you will find out there is a main program here. Okay, and if you scroll down, you will find out a lot of things that happen here, but you don't have to use all kind of this stuff at all. Then you can erase it and you can make clean main program, as I show in this one. Our main program is clean, so we just initialize I equal to 0, then we have the infinity loop. Here's just y1 and I++ and nothing else. Okay, and you can do one more cleanup to make your C file have just only this one. So we have 3 include in our systems. It's called standard def.h. We have STM32F10X.h, and we have STM32F10X underscore configurations.h. We need 3 these configurations in order to control our GPIOs. And don't worry about our standard peripheral libraries or SPL is already inside this one. So if you know how to use it, this is the way that you use it. Then our main program is here, so you just clean this main program and put your code into here. Then you can do anything you want with your microprocessors. And for the examples, this is the same LED example using the SMBs. So the LED example, what is it? It means that we connect our GPIO to a lot of LED, right? Then we would like to create increase one by one and display on LED. And by using this code, it's very simple. First of all, we just include 3 files here. Then we create our delay functions. In this one, we just call my delay. Then we just pass through our count numbers. Then in the loop we just reduce the count one by one until count is reached zeros. And that's it. It's just a waste of the time. Then our main program, what is in our main program? First of all, we would like to control our GPIO, right? So we define the variables is called GPIO initial structures, and this structures or these variables as an object or as a class is the class called GPIO initial type def. Okay, we have the new variable that we use this variable to configure our GPIOs. Then because if you do nothing, this startup inside your SPL library will push your CPU to the limit is 72 megahertz. But in this case, I would like to make something very simple. Then I use RCC deinitialize, and by using this one, they will force your CPU back to the default. It means that right now your CPU will use HHI oscillators inside your CPU, and also they will use your system's frequencies as 8 megahertz. You don't use PLL for boot up speed or anything. Okay, so we just do one more declarations is we call count equal to 0 and we identify as integers. Then we would like to enable the clock for GPIO peripherals. Then we use RCC APB2 peripheral clock command, and we say that we would like to enable the clocks for RCC APB2 peripheral GPIOA. In this case, it means that we use GPIOAs, and by using this one, you enable a clock to this GPIO. Then this GPIO is ready to be used. Then what else you have to do? You have to specify the mode and also the pins for your GPIO, right? Then you use this variable that is a class, right? GPIO initialize structures, and you dot GPIO pins, and which pin you would like to use. In this case, we did not use all our 16 bits, we use just only 8 bit, right? So you specify GPIO 0, or GPIO 1, or GPIO 2, 3, 4, 5 until we reach GPIO 7. Then by using this one, you will know exactly GPIO 0, 1, 2, 3, 4, 5, and 7 will enables. Then you specify the speed of your GPIOs in this group, and you say that your speed is 50 megahertz. And I will show you something that if you just specify the speed is 50 megahertz, but your CPU run on 8 megahertz, it's fine, right? Because you cannot go further than 8 megahertz, that's fine. But you can make it like a GPIO speed as 1 megahertz to follow your clocks inside your CPU is fine for you also. And in this case, I just paid it like a 50 hertz. 50 megahertz is fine. And we would like to use all this pin as output push pull. Then I just specify by using dot GPIO mode and equal to GPIO mode out push pull as shown here. Then finally we do a GPIO initialize, and we pass the GPIO that we would like to do this initialize, and this in this case is GPIO A, and we pass this variables, but this one is a structures or the class, right? We have to pass the address into this function. And by using this command, then you will find out that your GPIO A0 until GPIO A7 is the output push pull, and the speed can up to 15 megahertz. Then what else do we have left? We just do nothing. We just do a while loop here that is the infinity loop, and we do count plus plus. Okay, we increase the count variable one by one, and we write that count numbers into GPIO A using this command. We do GPIO right, and we specify GPIO A, then we follow by count. Then GPIO A will change the value according to your variable count. Then we do some delays. In this one, you can take a look and you will find out these numbers is totally different from the last time that you use assembly language, because this one when you go to my delay functions, you will find out if you change that one to assembly language, you generate a lot of line. Then you will find out these numbers is different if you would like to make your system run on like a 1 megahertz 1 seconds or 2 seconds. It's very You have to try by yourself, or what is the value for this one. Okay, but don't forget one thing, that everything I explain here, you have to write out your program inside your True Studio projects. Otherwise, it's not gonna generate anything for you. It show a lot of errors if you just follow this code by using just C language directly. Okay, so this is the main program that we have for our systems. And how can we create the output file or binary file that suitable for our CPUs? You have to do this. You have to go to the left hand side and click on your project's name. In this case, I call my project is called test1. Then I just right click on the project name and to go to the properties. Then when I click on properties, they will pop up this window for use, and you will take a look on settings, and you go to the last thing is called output format, and you click on here's create convert output build output, and you have to specify the format of your output or your of your binary file as an Intel hex. Then you just click OK. They will do nothing. Then you have to build your projects. You go to the projects and you just click on build a projects. When you build projects, you will find out there's a lot of things happens and they show up in the console here. And finally, if they show no errors, they will say build finish. Then they will find out converting build output to hex file and output sent to test1.hex. Okay, and you have to take a look what is your workspace locations, and you can go through that one. In this case, I see programming's AutoLix to Studio, and we have IDE and a lot of things showing here. I just go through that folders. I will find out I have something called test1.hex, and for the test1.hex you can copy it, then paste into your desktop. Then you can use the software that you used last time to program this hex file into your CPU. Then your CPU will run they show the same behaviors as our assembly language that you use maybe in your project 1. Okay, this is how we use C language for standard peripheral libraries, and we will use this a lot in this class. And also, if you prefer your own C language, is fine, or if you prefer your assembly language, everything is fine. Okay, so we move to the most important things in this today's is a project 2 explanations. For the project 2 explanation, I would like you to control 7-segment 4-digit modules as in showing here. And this one you can take a look at. There are 4 7-segment digits. The first one we call digit 1, 2, 3, and 4. And this one you need 8 bit to control, and each bit it belongs to A, B, C, D, E, F, G, and also the last bit is go to something called dot point. Is a point is shown in here. Okay, so this is the structures of this 7-segment 4-digit modules. As you can see here, they do what? They just use share the line as an input for A, B, C, D, E, F, G, and D, P, right? It means that every single digit on 7-segment they share A LED, B LED until DB LED, and they combine the other sides of LED together and create the output, one output here. These structures we call common cathode. Then if you would like to dry or to make your LEDs bright, then you have to specify the value for A, B, C, D, E, F, and G, right? And this one we will pass logic 1 if you would like to make that specific LED blink or bright. Then for the digit here, you have to place into the zeros in order to make your current can flow into the LED, and LED your LED will bright. Okay, by using this concept, we will find out if we connect our board to these 7-segment modules as shown in here, and you can take a look which pin numbers do what as shown in here. Then you will find out that by using these schematics, your GPIO will be used to create your character patterns such as number 1 to 9, and GPIO B bit number 12, 13, 14, and 15 will be used to on and off your 7-segment digit. It means that GPIO 12 will control this 7-segment. This one will control 7-segment. This 7-segment. This one will control this 7-segment, and also this one is control this 7-segment. But how can you control it? If you would like to make that specific 7-segment on, then you just use logic 0. But if you would like to make that 7-segment off, you just specific logic 1 into this pin, then your 7-segment will follow that command. So let me conclude that by using this one, if you would like to create patterns or characters inside your 7-segment, you use GPIO A, and A is share. Port A is shared for all the 7-segment. Then you have to specify which 7-segment you would like to show that patterns by using GPIO 12, 13, 14, and 15. If you would like to make that pattern appears on that specific locations, then you have to make that pins equal to 0. Then they will display. So let me explain one more things. Okay, this is my my fault, because I just give you the wrong IC part for your 7-segment. If you already bought it from es.co.th, then you have to buy it again. I'm so sorry. But if you don't have money, you can ask me for refunds. Okay, just only 50 baht, 50 baht. So that's fine. You can come to the class and ask me, okay, give me back the money. That's fine. But you have to buy this one. Okay, you have to buy this one for this project number 2. Okay, you can select this one, which one is fine for you is okay. Then I have to specify a little bit more in this one. So if you would like to create a patterns is one on your 7-segment, then you provide GPIO A equal to 0x06. They will show pattern 1 here. And if you would like to make pattern 1 appears on your digit 1, then you make GPIO B 12 is equal to 0, and you make everything else equal to 1. Then logic 1 will display this one pattern for you only, and the other thing is just dark. If you put GPIO A is equal to 0xFF, they will display number 4 as I show in here. And if you specify GPIO 14 is equal to 0, and you make everything else is equal to 1, then you try to show these patterns on your segment on the digit 3. Then the digit 3 will show 4, and everything else is dark. Then if you have 4 pattern here, 1, 7, 4, and 6, and you can follow by this one appear on the digit 1, 7 appear on digit 2, 4 appear on digit 13, 4 appear on digit 3, and 6 appear on digit 4. And if you create the patterns show 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 fast enough, so what's gonna happen? If you display 1, 2, 3, 4 step very fast, or fast enough, or greater than 50 Hz, then you will find out every pattern that show in your specific locations of your 7-segment will appear at the same time as I show in this one. Why? Because your eye cannot find the difference of the, you cannot detect anything that change more than 50 times per second. And in this case, if you create your software that display 1746, 1746, 1746 at digit 1, 2, 3, and 4, and you create this loop very fast, then everything will appear for us is 1746 like this for us. Then this is the example how can you create your code for the project 2. And what actually project 2 would like you to do? First of all, I would like you to write program in C. Okay, you can try SMV. It's fine, but you will find out you will suffer for it. Okay, but this one is not that suffers, but you can try it at home. But this one I would like you to familiar with your IDEs. Then I would like you to write everything in C. Then at the beginning, when you start your software, they will show 777 on your 7 segments. Okay, after 2 seconds, you have to display the last 4 digits of one of your group members' student IDs. After 2 seconds, after that, you have to display the first 4 digits of one of your group members' student ID. Then after 2 seconds, you display the last 4 digits of the summations of all student ID together in your group. It means that you have 3 members, right? You just combine, you just summarize these 3 student ID together, and you use last 4 digits to display on this 7 segment. And finally, after 2 seconds, you have to display bar, 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 bar. Then you go back to step 3 in this one and follow to step 6 and so on and so on. Then it will display your last 4 digits for one of your member group, then first digit and last 4 digits for summations, and bar, 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 and go back to display your last 4 digits of one of your member group, and we will show this continuously. Okay. Because right now we are on time on our times, then the project number 2 you have to submit in the class on the 5th of November this year. Okay, as I show here. Okay, and this is display that I show you 1, 2, 3, 4. Okay, and if you have problems in order to create this kind of things, or you don't clear actually what happens, I already give you the books that I wrote, but it's not a perfect yet. Okay, it's just draft versions. You can take a look in that one, then you can follow the step by step, and you will get the idea how can you create the patterns on the 7 segment modules like this one. Okay, and that's all for today. Then this is the end of our chapters in GPIOs. Then for the next time, I will talking about the serial communications and also ADC module, and you can think of your projects number 3 and number 4 after that. Okay, until next time we met, stay free from COVID and enjoy your life. Good day.